Okay, so we've figured out this individual's probability of being a carrier, and now it's time to tackle this individual. Let's draw out the little Punnett square like we did before and assess what types of offspring can come from this particular cross. And you'll see that this one's actually the simpler one. We did the more challenging one first. So we'll put big A across the top, big A, little a down the side, and you'll see that half of the offspring are carriers and half of the potential offspring are not carriers. So each of these again has a value of 1/4 based on using the product rule to apply to the gametes as they come in. So the probability that this individual is equal to 1/2. Now you might ask the question, well, why aren't we normalizing here in this situation? And the reason is we're not normalizing because there's nothing that we've eliminated. There's nothing based in this little Punnett square that we know for sure is not this individual's genotype. So there's no normalizing here. Normalizing is all about eliminating a possibility based on a phenotype and then readjusting the remaining probabilities to be normalized to what's remaining. Okay, so then the next question comes, now that we have these probabilities, how do we carry on from here? So the probability that this individual is a carrier is equal to 1/2. Now things get a little bit more challenging. Now we have an individual that we're crossing with another individual that we don't know for certain what either of their genotype is. So the way to set this up is to use the following matrix. So let's take 2-2, this individual here. They might be big A, little a, and that has a probability of 2/3. Or they might be big A, and that would have a probability of 1/3. Now 2-3 also could be either heterozygous or homozygous dominant, except now the probabilities are 1/2 and 1/2. So this actual mating might have been one of four different possibilities. Could have been this with this, this with this, this with this, or this with this. And it's just a question of the probabilities that are involved. The way to represent this is to use this matrix. And I'll just have to erase this to get more space to show you how this works. So if indeed it was this particular cross, we can draw a small Punnett square for that particular cross. In this case, that would be what was results. If it was this particular cross, and again, each of these crosses has a certain probability that we've just worked out. I think it's fairly easy to see in this particular instance that all of the offspring would be homozygous dominant. Okay. Now, it could have been this cross. In this case, we need big A, little a, and then down here we need big A, and you fill it in. Okay, and then the last option is this one up here. So we'll put big A up there, big A, little a there. It doesn't really matter which parent you put in which side of the Punnett square, as long as you make sure that you're not mistakenly putting the same person down twice. And then you fill in that Punnett square. Oops. There we go. Third time's the charm. Okay, so this is a graphic representation of all the different possibilities that come out of this specific cross. The question now is, how do we assign a particular probability? And this is where the sum rule and the product rule come in handy again. So I'll just make myself some more space here again. And we could ask this question. What's the probability of the offspring of this cross? So if you look back at your pedigree, this is now the individual at the bottom of the pedigree that we're figuring out, the diamond-shaped individual in the pedigree, to figure out what the probability is that they would have one of these genotypes. So this is individual 3-1. And we could ask this question here. What's the probability that they are little a, little a? Well, if we look through this whole matrix, there's only one way for this individual to be little a, little a. And actually, as you'll see, we didn't need to do this full treatment for this specific question, because this way, for this particular genotype, there's only one way that this genotype could be formed. What are the requirements? 2-2 needs to be a carrier, and 2-3 needs to be a carrier, and each needs to contribute the little a allele. So we could say, what are the requirements? 2-2 is heterozygous. 2-3 is heterozygous. 2-2 passes the A allele. 2-3 passes the A allele. This has a probability, as we figured out, of 2/3. This has a probability of 1/2, as we figured out. And then the probability that, assuming that they are a carrier now, right, because this is part of the probability or the requirement list to say they need to be a carrier and they need to be a carrier, and then assuming they're a carrier, they pass the little a, so it's already worked into that probability. This has a probability of 1/2. This has a probability of 1/2. And because we say and between each of these steps, the final probability for this individual to be little a would be 2/3 times 1/2 times 1/2 times 1/2. Okay, so 2/3, 1/3, 1/6, 1/12 is our final answer for being little a. Things get more complicated, of course, once we start asking other questions. We could say, what's the probability that 3-1 is a carrier, is heterozygous? And that's what we'll turn to in the next segment.